So now we have module 4, 5, 6, 7 left. 5 is a pretty small theory module, so there's very little to look at. Basics of vectors and matrices. Distance is root of a square plus b square if your points at a comma b. Between 2 points, x2 minus x1 the whole square, y2 minus y1 the whole square. Take the root of that. Matrices we already know. All of this is just fluff. So it's fine. Angle between two vectors is theta. That's also fluff. Doesn't matter. Data representation is some theory you need to keep in mind. So the leftmost column you see here is a sample. This is the length, width, petal length again, and petal width are features. And this is a class label, basically something that you are sorting these samples into. So based on these features, you classify them into separate classes. That's what this mathematical expression means. The second is data preparation. There's a process of cleaning and transforming raw data prior to processing and analysis. Involves reformatting, correcting, combining data sets. Why do we do this? We want to transform data sets so that information is more accessible. This is done in a few ways. So the first is data cleaning. That is, you fill in missing values, you smooth noisy data, you import data sets, you merge them, you identify the errors, and then you remove the duplicates. There are a few ways this can be done. Measure of central tendency, which is you identify the mean of the duplicate data, and you remove the closest ones to that, or the most probable value. The second part of data preparation is data integration, which is you merge from multiple data sets, and to prevent one data set from being much larger and having a much bigger influence than the other, you normalize them. This is done in two ways. The first is min-max normalization. So these two are where most questions will come. So it'll either be a question based on these two, or it'll be a question based on the theory here. So the first is min-max normalization. And here, what you have to do is essentially, so let's look at this data representation table, for example. Let's take one column, the length of the petal. So here, your V dash would be 1.4 minus min of V. So that would be the minimum value in this whole column, which is 1.4. So 1.4 minus 1.4 would be 0. So V dash would be 0 there. For the third row, for example, if it's 4.5, then you're probably going to, not probably, you are going to take V dash is equal to 4.5 minus 1.4 because that is a minimum value in this column. And you divide that by max minus min. Here the max is 5, the min is 1.4. So you do 5 minus 1.4 in the denominator, and that's your V dash value. So this, you compute this for every entry in every column. And this is how you arrive at the table for min max normalization. Similar to that, Z score normalization has a different formula, but it's the same process. So here, your V dash is going to be V minus V bar, which is the mean, so the average. So of this column, the average would be 1.4 plus 1.4 plus 4.5 plus 5 divided by 4. And then you divide the whole thing by your sigma. Um, the formula for sigma is given here. It's the summation of Vi minus V bar the whole square divided by n, and then take the root of everything. So these are two ways, and you will probably get a question based on either of this. So a little bit later we'll discuss the question um, formulation for this. But the third thing to look at in data preparation is data reduction, which is you reduce irrelevant data, you reduce dimensionality, and you store only relevant information. The final thing is dimensionality reduction. Could be lossy, could be lossless, some more fluff theory that will probably not be asked, but this is only purely theory module, so worth keeping in mind. Then we go to module 4, which is uncertainty. So why does uncertainty occur? It occurs because there is incompleteness and incorrectness in our understanding of in the understanding of an agent with respect to their environment. So they don't know their environment fully, basically. So this could also be because of practical ignorance or just not knowing things. So the difference between logic and probabilistic reasoning is that in logical reasoning, your belief is always going to be either true or false. In probabilistic reasoning, um your thinking is going to be in terms of a degree of belief between 0 and 1. So if you believe something a lot, it's going to be 0.9. If you believe something, but you barely believe it, it's going to be 0.1. A bunch of probability rules here that you probably need to know. You probably already know all this. But okay, what are priors? They are beliefs that are both unconditional and prior to new evidence, right? So something that you have already kept in mind. Um, Conditional probabilities are defined here. So P of A given B is equal to PA and B divided by P of B. An example here is just joint probability. So you look at this table, it's pretty clear to infer that the sum of the row comes up to point 1 here, 0.9 here. That sums to 1 as a total, sum of all probabilities. That's what joint probability is defined as. So we've inferred a few probabilities here. So P of cavity or toothpaste. So that would be this column as well as this column, because toothpaste is this entry is cavity. So that's how it would add up, as well as this, because cavity, toothpaste, is a common element. 0.04 plus 0.01, 0.06, sum of that. Chain rule of probability. You don't really need this right now, but it's useful to keep in mind. P of x1, x2, dot, 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 xn is equal to the product of every entity of I, where P of xi, x1 till x1, xi minus 1. Here's where Bayes theorem comes in. We know P of A and B is equal to P of A given B times P of B. But we can also reverse this and say that, oh, P of P and A is equal to P of B given A times P of A. So what we do is we equate it and divide the whole thing by P of A to get the Bayes theorem, which is probability of B given A is probability of A given B times probability of B divided by probability of A. So there's a quick example here showing how Bayes theorem actually plays into effect. So this is what is used for this is the basis for questions in this module. So there are three examples that we'll discuss: burglary situation, the fuel situation, and the heart disease one, to understand Bayesian networks better. So Bayesian belief networks are basically a part where you have a new burglar alarm that sometimes responds to minor earthquakes. John and Mary are two people who are your neighbors. They call you if the alarm sounds, but Mary has an issue where if she misses some, she can miss some alarms because she plays loud music. John also has an issue where he always calls, unlike Mary, but sometimes he confuses his phone ring with the alarm, which means both Mary and John can call you even though the alarm isn't actually ringing, or if the alarm is ringing, they might not actually call you. So the first thing we try to find is, given the call arrives to you, what is the probability of burglary? And we have a bunch of probability tables given here. So the first is P of B is 0.001, P of E is 0.002. So these are basic probabilities that we have. This is the probability of a burglary happening. It's 0.001, probability of an earthquake happening, 0.002. Probability of Mary calling is given by this, where probability of Mary calls given an alarm is 0.7. Given that alarm doesn't happen, Mary calling is 0.01. John calling, if there is an alarm, then 0.9, and if there's no alarm, then 0.05. So there's another table here as well. Probability of alarm ringing given there is a burglary and an earthquake, and we have the variation in burglary and earthquake here. Now, the probability of alarm, but neither burglary nor an earthquake happen, and both John and Mary call. So the first thing we do is mathematically describe the situation. And that is illustrating all dependencies that exist, right? So here the dependency starts from this. That is the lowest dependency, P of John given alarm, John calling given alarm, and Mary calling given alarm. So we write that down first. And then the next dependency that we have is this, which is probability of alarm given that there is a B and there is an E. So that is a dependency that we write next. And the next is the topmost, which is probability of burglary and probability of earthquake. So we write them in reverse order from bottom to top. And essentially what happens is here, since we have neither burglary nor earthquake, we're going to take not B and not E. And here we have both John and Mary calling. So we will ascribe those probabilities as true. And we just end up multiplying all of these from the tables that we have here, 0.9, 0.7, etc. You can just read them and you'll figure it out. But yeah, that's pretty much how you calculate that. Again, probability of John calling is going to be the second question that we look at. So mathematically, probability of John calling will be probability of John calling given alarm times probability of alarm plus probability of John calling given that there is no alarm times probability of no alarm is elementary probability that I did not know before writing this. So I'm just going to go ahead and say that anyway. And then you expand all of them. So probability of John calling given alarm times probability of alarm expands to again probability of alarm given burglary and earthquake times probability of burglary and earthquake, and then you write the negation of that, then you write the negation of E, and then you write the negation of B and E, and then you do the same thing for this. Honestly, here you're better off like watching the video of Mahesh Siddharth or like someone else on YouTube who solved this question. Um, so the the final thing is probability of burglary given John and Mary both call. So here the question asks us for P of B given J comma E or J comma M. So the factorization that we earlier discussed, right? So when we're writing a factorization, we write from the most basic element upward. So P of B, P of E, P of A given B E, P of J given A, P of M given A. And then we apply the Bayes theorem and then we sum all the hidden variables here. So for now, just ignore this. The same principle is used in the next two questions and is probably better explained there. So the second question is batteries. And we have a fuel gauge here. And the two variables it depends on are battery and fuel. Probability of battery being bad is 0.1. Probability of fuel being empty is 0.2. The probability of the vehicle starting is also dependent on both battery and fuel. So we have this table given to us, probability of GMT be good, and then like just fill in the values here. We have this table. We also have this table given to us whether the vehicle is good to start or not. So these are the two tables. And we are asked to find the probability of B, the battery being good, the fuel tank being empty, the gauge being empty, and the vehicle actually starting. So again, we do the same factorization that we did. Um, so probability of B, probability of F, probability of S given B comma F, probability of G given B comma F. So here we substitute the values. So we know that B is good, F is empty, G is empty, and S is yes. So we substitute all of these here and we get 1 minus 0.8, 0.2, 0.8, 0.9, and this is basically what we end up with 0.028. So the second question we are asked is find probability of B battery being bad, fuel being empty, gauge being not empty, and the vehicle not starting. So again, we take all of the probabilities and we substitute. So the same factorization we take, substitute S equals no, G equals NE, then we compute the probabilities from this table. So just a small note, if S is yes here, and B is if suppose we're computing probability of starting is yes, given battery is good and fuel is non-empty, then you have to subtract this from 1 because the probability of S being yes given this whole thing is 1 minus whatever probability is here. So similarly for any of these rows, if start is yes, then you just have to subtract from 1. Same here, right? If the G is non-empty, then you have to subtract from this column of values. So that is how you calculate this sort of question for this sort of question. The third type of question is given that the battery is bad, find the probability of the vehicle starting. So we mathematically express that as probability of S is equal to yes, given that B is bad. So here we notice that we have two variables given to us. That is, we don't have G and F described. So GF is hidden. So what we do is we apply the same factorization, but we add a summation wherever the variables are not given to us. So since G and F are hidden, we add a summation F, summation G in front, and do the factorization the same way, right? So the rest of this is the same as this expression that we originally derived, except we're adding two summation signs here. But notice that S here is not dependent on G at all. So we don't really care about the gauge right now because we're calculating the probability of the vehicle starting given the battery is bad. There's no direct dependence, right? The dependence here is between the battery and the fuel and vehicle starting. So we don't need the gauge term. So we just throw that out. Then we simplify it to these three terms alone, right? And then we substitute the same value. So S is equal to yes, B is equal to bad, and we have only one summation now because we've thrown the G summation out. So we'll notice that we have two values plugged in, but obviously we haven't been given F. So what we do is we compute this expression for when F is empty and for F is non-empty. And you sum both of them, that gives you 0.008. So what you'll notice is this is the computation of probability of S is yes and battery is bad, but in conjunction. That is, it's the probability of S equals Y comma B equals B. And if you remember Bayes, then probability of S given B is probability of S comma B divided by probability of B. So we take the 0.008 divided by probability of battery being bad, then arrive at 0.08. That is the answer. The final example for this is heart disease. And again, we have a bunch of dependencies, right? Exercise and diet are what heart disease depends on. Um, but also we have heartburn here. Heartburn depends on diet. BP depends on heart disease. Chest pain depends on heart disease. Heartburn depends. Heartburn directs chest pain. So there's a bunch of probabilities here. Probability of exercise actually happening, exercise equal to yes is 0.7. Probability of diet being healthy is 0.25. And then there's a table here of heartburn actually happening. When diet is healthy, there's a 0.2%, 0.2 chance of heartburn being yes. Then when diet is unhealthy, is a 0.85 chance of heartburn being a yes. Obviously, if you want heartburn is no, then you'd have to do 1 minus 0.2 is equal to 0.8. We also have a table for blood pressure. That is, blood pressure is high. The probability of blood pressure being high when HD is, which is heart disease, yes, which is 0.83. And when there's no heart disease, it's 0.2. We're also given two more tables here. So Y indicates yes, H indicates healthy, N indicates no here. So these are the tables we're given for heart disease and chest pain, dependency tables. So the question is find the probability of heart disease given that the person has a high blood pressure. Again, we write the same characterization, the factorization, right? Probability of D, probability of E, probability of heartburn given D because the dependency exists, probability of heart disease given E and D because the dependency exists here, probability of blood pressure given HD because that's the dependency here, probability of chest pain given heart disease and heartburn because that's what chest pain depends on. Again, this is a factorization we arrive at, and we need to find the probability of heart disease being yes if high blood pressure exists, which is also yes. So for this, again, so if you recall, here we've tried to calculate P of S comma B to evaluate P of S given B, because we later divide by P of B equals B. So we do the same thing here. We want to find P of HD comma BP. And again, we have the missing variables D and E. So we take them out, we add the summation point, and then we include all the terms. Again, here we need all the variables, so we'll include all of them. So probability of D, probability of E, probability of blood pressure given heart disease, and probability of heart disease um, given the diet and exercise happening. Obviously, we do not really care about heartburn and chest pain, so we don't include those expressions here because those dependencies don't exist in this part, which is what we're looking for. And again, we evaluate this for all four values of D and E, right? So can be high, D can be healthy, non-unhealthy, which is H and U. E can be Y or no. That is excess can be yes or no. We calculate that basically the product of these probabilities from these tables. And we arrive at these four values. We sum them, we get 0.4. And again, we do the same thing for HD equals no, because when we are asked to find the probability of heart disease, we also have to find the probability of heart disease not being there. So the sum is zero point 0.1 for heart disease equals no. The only difference here is instead of heart disease equals yes, we do no. And when we do the same four computations. So here it's 0.4, here is 0.1. So what we have to do is for the final probability, we multiply yes, then divide that by the sum of yes and no. So zero point 0.4 by 1, zero point 0.1 plus zero point 0.4 is zero point 0.8. That is your answer. And that is that the end of the module? No, it's not. Um, there's only so Markov property isn't much. It's just a bunch of theory that we'll look at hidden Markov later. Decision networks are something. Okay, so we'll look at the theory here. We'll solve the question in the next video. But basically, decision networks are under uncertainty. You have a degree of beliefs. Agents want to maximize utility. So you can safely ignore this expression and look at this question instead, right? But before that, some notation. The circle implies a chance node or a variable. The rectangle implies a decision node or an action, and the diamond implies a utility node. So if you take here, you have an example, right? Take or leave is a decision node. An umbrella, the umbrella is what you're taking or leaving. The weather is a chance node or a variable that can change. The probability of rain is 0.3. The utility node is given here. There's a bunch of probabilities given here. Now, the domain for chance is sunny and rain. So the weather can either be sunny or it can rain. Similarly, the domain for an action is you either take the umbrella or you leave the umbrella. So the way you calculate expected utility is, so the expected utility is always for an action given that some variable occurs. So the probability of your action given that weather is some way is evaluated as such, right? So expected utility of you taking the umbrella given that there is sun plus expected utility of you taking the umbrella given that there is rain. So that accounts for the probability of action one, which is take. So you use this table to arrive at that and you calculate that. Similarly, you use the expected utility of leaving and you sum both possibility of leaving. So you can leave the umbrella when it can be sunny, you can leave the umbrella when it's raining. So expected utility of you leaving it when there's sun is 100, but wait, no, leaving it when there's sun is 100, but again, it's wait, leave. Yeah, 100 times 0.7, 1 minus 0.3, and then the rest is 0, so it's just 70. So here, the maximum of both of these is 70, so the maximum expected utility is defined as 70. Now, value of information is when you get new information that makes a significant difference to the optimal course of your action. It also depends on the likelihood of the various outcomes that you have. So let current knowledge be E, let the current best action be alpha. This is the expression that you have. So basically, you can ignore these two safely. The value of information is the difference between the maximum expected value when you have new information and when you had the old information that you had. So I'll go through a question in the next video when we're going over modules 6 and 7, but that's pretty much all for this module.